or your assignment from last time and take a peek at it. We'll take some questions, if there are any. Happy to do a couple as examples, or let me know. Joey?
Can you do number 5, please?
Number 5?
Yeah.
Sure. So we have to do a prime factorization of 1575. So I'm going to start by observing that since it ends in a 5, I certainly know it's divisible by 5. So that gives me 5 and 315, and I know 315 is divisible by 5. And that gives me 63, which is 3 squared times 7. Is that okay? So I didn't write out the factor tree. I just kind of did it on my calculator and wrote down the result. So 5 squared is a perfect square, so the 5 can come out front. 3 squared is a perfect square, so the 3 can come out front. And it leaves me with just the 7 left underneath the square root. And then I could multiply the 3 and the 5 and 7. And notice here that I'm kind of shortcutting some of the steps, right? Like I'm showing a little bit less than we did where last time I showed like every little nitty-gritty little detail. And now I'm just kind of giving milestones. And you're probably thinking like, dude, why didn't you like show us to do it that way before so I didn't have to do all this writing last time? And I did it intentionally to try to get you to do all the writing last time so that like when I start doing the skipping steps, you understand the blanks that I'm skipping, right? So it's a little bit easier to follow when we start becoming a little less, kind of giving this work summary rather than like every single little step. Pete?
Another test, are you looking for the factor tree?
No, I would not need to see that. Again. Absolutely. If you write the prime factorization, that's all I'd really need to see. I don't need to see how you got that, since all you're doing is just like basic arithmetic, Reese. 9? Certainly. Okay. So again, we'll start factorization. So I'll take the -1 out first. 750 is divisible by 2. So that's 2 and 375. 375 ends in a 5, so I know it's divisible by 5. So that gives me 5 and 75. And 75 is 5 squared. So that's 3 5s now total, times 3. So I know the cube root of -1 is just -1, so I'm going to take a negative sign out front. The 5 to the 3rd is a perfect cube, so I'll take the 5 out front. And that leaves me with just the 2 times 3 left underneath the radical. And I'm done. Does that feel okay there? Pedro.
Number 15.
Yep. Sure. Okay, come on. So I'm going to start by doing the prime factorization and just putting it all under the same radical. So I have -1, and then 12 is 2 squared times 3, and then 10 is 2 times 5. Okay there?
Yes.
And if I look, I have 1, 2, 3 2's. So that can come out along with the -1. And I'm left with underneath 3 times 5, or 15.
Is that easy?
We can make it that easy once we understand what it is that, like, how we're pulling things out and not pulling things out, which is why we did all the work shown last time. But I'm okay with just like, if you have the prime factorization and then like show me what's being pulled out and then write the answer, that's good enough. Eventually these numeric ones should be ones that we can like really do not a lot of work once we have the prime factorization. That's the goal that I'd like to get to for us, is comfortable doing that. But understanding like how we're pulling things out, I had to do like all the symbol pushing last time, which is probably what you did in your homework, which was what I expected. So as we get going further in this chapter, we can pare down on the amount of work we're showing, because we really don't need it anymore because we understand what's going on, and we can kind of skip some of those steps. Yeah, this seems so easy when I do it because I didn't write anything down. But like, there's a lot of stuff going on behind the scenes that if we didn't write it all out beforehand, skipping all that stuff, you're just like, wait, why is that coming out? Like, what's going on? Where now it should be doable in that way. Reese. 20? Sure. So I'm going to kind of do it the same way. So I'm going to do my prime factorizations. And I'm going to do it like all under the same thing. So 343 is 729 is 9 to the 5th. Oops, 3 to the 10th. 525 is 5 to the 3rd. Oops, I still have a -1 in there. Let me write that in there. Okay. So 729, I believe. No, that can't be right. I'm so stupid. It's 3 to the 6th, right? Let me just, yeah. Oops, 3 to the 6th. Sorry, thank you. Good question. I looked at him like, no, that's way not right. Yeah, 3 to the 10th is big. Okay, so let's take a look. -1 can come out, right? It's just -1, so I'll take the negative sign out. I to the 3rd, so that's a 7 cubed. That can come out. I have 5 to the 3rd, so the 5 can come out. And if I think about 3 to the 6th, that's 2 3 to the 3rds. And I have nothing left, right? So this is just, oh, that's not right. It's too early. 315. That's it. Is that okay, Reese? So again, I'm just looking for packets of 3 on the cube root. If it has a packet of 3, it comes out. And if it doesn't, it stays. And we just, everything that comes out gets multiplied together. Everything that stays in gets multiplied together, and we're done. Now, I didn't want to start that way because that doesn't make a lot of sense. But after we did what we did yesterday, we can kind of compact all the work down into like something that is quick. But still we understand what's going on, even though like there's a lot kind of machinery going on in the background that we just aren't going to write down anymore because we don't need to. We understand what's going on, and like we've shown enough here to show, to explain to an informed reader what it is that we did. Reese, you feel good? Does this start to feel better? I know you said you weren't sure about last night's homework at the start of class. Does that feel more manageable when we stop, or when we condense the work down, it's just a lot less writing? All right. So we feel okay then? We'll move forward? Okay, cool. Yeah, some of them could get big for sure. So we're going to continue talking expressions. Last time we talked about reducing radicals and multiplying. Today, okay with that plan? So we have two topics to talk about today. Dividing is a natural extension of multiplying, so it's not so bad. And then adding and subtracting is different, but I think in a way even easier. So examples and talk through some of the things that we have to be worried about and not really give any like abstract general formal notes on this. We're just going to kind of do some example problems and talk about kind of what we're doing and why we're doing things as we go. Is that okay with you guys? Okay. Oops. So dividing is what we're going to do here. Let's say we have the square root 6 divided by the square root 2. If these are the same kind of radical, in this case they're both square roots, do this. And just put them both under the same radical. The advantage of doing that is that I notice that 6 and 2 reduce, right? What's 6 over 2 reduce to? 3. So we're done. Because the square root of 3 can't be simplified anymore. That's it. So if we notice that I can reduce the fraction, we can just combine the two radicals together into one fraction, do our reducing. And maybe there's more to do after that. Maybe there's not, like there was in this case. Let's look at another one. So let's say we have the square root of 18 over the square root of 50. So again, 18 over 50 we should notice can reduce because both of them are even, right? Now 18 and 50, hopefully we see how would those reduce? Yeah, 9 over 25. You divided both of them by 2, right? If you didn't notice that, you could always do a prime factorization. Is 2 times 3 squared, and the prime factorization for 50 is 2 times 5 squared. And you could notice the 2's would reduce, just like. And you're left with 3 squared over 5 squared, or 9 over 25. Either is fine. We can then break that back up into 2 separate radicals, because I noticed that 3 squared, the square root of 9 is just 3, and the square root of 25 is just 5. So there, after we reduced, there was still a little bit more to do, but, not that much more to do. Is this so far so good? Does it get worse than this, other than the numbers getting inconvenient, right? Sure, it could. Let's say we have square root of 27 over the square root of 32. Can the fraction 27 over 32 reduce? I mean, if you're not sure, what should you do? The prime factorization, right? Because we're going to need that anyways, probably to do the problem. So let's go ahead and do that anyways, right? 27, 32 is 2 to the 5th. So can there be any reducing I can do there? No, right? Rather than one big radical, because there's no fraction to there's no reducing to do in that fraction anyway. So Pedro?
Could you also do like 10 and 3?
Yeah.
And then
Yes. Yep, that would be fine also. So as Pedro's pointed out here, 3 cubed is the same thing as 9 times 3. Right, because this is basically 3 squared times 3. 3 on the outside, and the regular 3 is left on the inside. Similarly here, 2 squared, and 2. The 2 squareds side, and the 2 to the first is left underneath. Is everybody okay with that? Equivalent to doing 9 times, same idea. So that gives me 3 root 3 over 4 root 2. Now here's the catch though, folks. We're going to get our answer finished in that case. You probably remember that from geometry course last year when you talked about like sine, cosine, and tangents. When you wrote those ratios, you didn't leave any fractions in the denominator then. Now that was a long time ago, but does anybody remember what you did to kind of solve that problem? That's okay. So it was a long time ago. What we do is the square root that we're trying to remove from the denominator, we're going to multiply to the top and bottom of our fraction. This process is called rationalizing the denominator. So in the numerator, I have 3 times the square root of 3 times the square root of 2, or just 3 square root 6. Everybody's okay with that? In the denominator, times square root of 2 times square root of 2, or 4 square root of 4, or 4 times 2. Is everybody okay there? And then now I want to point out to you that if decimal and this number into the decimal, they are the same decimal, much in the same way that like 1/2 and 2 over 4 are the same decimal, that those two fractions are equivalent because all we did, right? So we didn't change anything other than the way the fraction looked. We're talking about still the same number. Everybody's okay with that idea? Let's do another. Oops. I want that in the denominator. So this one, square root 70 over square root 80. Probably it's tempting to write this as just the square root of 70 over the square root of 180 and reduce it down. What can you notice you can reduce by here? 10, right? That should stick out pretty much like a sore thumb, and we can just write that as 7 over 8. Feeling good? Okay. Needed to. Okay. So then we want to rationalize our denominator. So we'll multiply the top and bottom by square root 2. we get square root 14 over 3 times 2, or square root 14 over 6. I want to point out to you, though, that notice we had to rationalize our denominator here. If we had, instead of reducing the way that we did, if we had looked at the prime factorization and were a little bit clever, we could have avoided having to rationalize the denominator in this situation. So let's just show you guys what I mean. So instead of reducing this way, what if we had written the prime factorization? So what we did above, we reduced the 2 and the 5, right? But notice in our denominator, we have a 2 squared and a 3 squared, which is good. I really only want to reduce the 5 here. I want to leave the 2. Is because 2 squared, I take the square root as 2. 3 squared, the square root is 6. Or I'm sorry, the square root is 3. And I'm done. No rationalizing the denominator needed there. So I want to point out to you that in some cases, it's a lot less work if we don't fully reduce our fraction. That if reducing our fraction gets rid of a perfect square, in this case, it was going to actually create more work for us than if we just didn't do all the reducing we could possibly do and left the perfect square there. You guys kind of see that? So, again, you will still end up at the same place, same answer, but instead of having all of it in here, we basically just had 1. Which is a pretty good trade-off, right? If you catch that. If you don't catch it, it's not a big deal. All you've done is taken the long way, the scenic route. Let's put it that way. That sounds less negative. You end up at the same place, you just got a little bit more scenery along the way. Me, I'm not about that life. Hey, Joe.
For the denominator, let's say it was 3 and then whatever, it's square root was 3. Multiply top and bottom by 3.
So you're going back and asking this part right here.
Yeah, like let's say that part was 3.
So we'll just label that as A. I would do that. Whatever that number is. Is that cool?
Yeah.
Okay. Just as an in general. Yep, that's what we're doing. So let's do some cube root examples here, because some of these things can change a little bit if we have a cube root or a 4th root or a 5th root or whatever. That we have to be a little bit careful about. Oops, I want black. Okay. So let's say we have the cube root of 54 over the cube root of 16. Now, after the previous lesson about maybe just reducing willy-nilly, that I really want to look at the prime factorization before I reduce my fraction in case I can avoid having to rationalize the denominator. And I can't really catch that if I don't do a prime factorization. Oops. And here I notice that there's a 2 that I could reduce, and it's not going to ruin any perfect cubes by reducing that 2, so let's go ahead and do that. Is that okay with everybody? So in the numerator, I have 3 cubed So when I take the cube root, I just have 3. In the denominator, I have 2 cubed. When I take the cube root, I have 2. So I'm done. Pretty cool. Again, we shortcutted through some work, but that's because we did all the heavy work yesterday so that we could hopefully shortcut through the work and still have it be understandable, right? Let's say that we have so let's say we have cube root 81 over cube root 4. Just like on the previous problem, I'm going to say 80 to the 4th squared. Now there's no reducing that so there's no reason to think about this as one radical, so I'll just leave it as 2 separate radicals. Everybody okay there? I can reduce the numerator, so I have 4 3's in there. I need 3 of them to bring the 1 to the radical. Is everybody okay with that? Again, you could think about that as like 3 to the 3rd times 1, or 27 times 3 if you want to think about it that way. It's still doing the same thing. Everybody's okay? I like to use the exponents, but if you don't need to. Can I do anything in the denominator, though? There's no reducing to do there, right? Because I have only 2 2's there. I need at least 3 to do anything. Now, we need to rationalize our denominator, right? What do I multiply the top and bottom of this by? Cube root of 2 or 2 squared or something else? Well, how many 2's do I need in a cube to get rid of the cube root? 3 total, right? How many do I have there right now? 2. How many more do I need then? 1. So I just need 2 to the 1st. Everybody's okay with that? So that would give me 3 cube root over 2. As we had cube root 2 denominator, when we rationalized, we would use 2 squared then, right? Because we had only 1 2 in our cube root. We need to get to 3, so we needed 2 more. Just as a hypothetical, right? So with the non-square roots, we have to be a little bit more careful when we rationalize the denominator, and we have to get to like, okay, how many more of these do I need to get rid of that radical? But that's it. That's as complicated as it would get. Does that feel okay for you guys? Should we talk about addition and subtraction? And just do some examples and kind of talk about how things work with the examples and not write down any like abstract rules or anything. We're just going to kind of talk it through and do it with examples. That seems to be working pretty well for you guys, so we won't try to be too abstract here. We'll be pretty specific. So the way this works is if I have 2 things that I'm adding together that have radicals, if the radical parts are identical, so they're both square roots, and the number under the square root is the same, we can add or subtract them. And the way we add or subtract them is just by using the coefficients. So this is just going to be 8 square root 2. The square root part doesn't change. It's just like when we add variables. 3x plus 5x is 8x. The radical part is x, kind of like a variable in that regard, right? Where it just doesn't change. Does that feel okay?
Mr. Cooley,
Yes, sir.
did you say you can only add them if the number under the square root is the same?
And the radical part is the same, yes.
Okay.
So, for example, if we had this, there's nothing we can do here because one is a square root, the other is a cube root. Or this one, again, nothing to do because one is a square root 2, the other is a square root 5, nothing to do there. So unless the radical part is identical, the same kind of radical, the same number under the radical, there's no adding we can do or subtracting. Yep. Well, what about this? Can I add these? Yes. And you're like, hold up the truck, Mr. Kulik. How is this any different than C, where you said there's nothing to do? Well, in C, there's no either of these radicals, right? Square root 8, though, can be reduced. The square root of 8 is 4 times 2. So that's really going to be 2 times the square root of 2. So they are the same radical, they just didn't look like it at the beginning. Yes, of course. Right, so there's always like a coefficient of 1 out front, even if we don't write it. Exactly right. Actually, write it there. Okay. Does that feel okay? Let's do one more, just to kind of make sure we got it. Or 2 more, or whatever, a couple more. But this is basically the only trick you have to watch out for. Is before you decide whether you can add the 2 things together or not, you have to make sure the radicals are reduced. Reese. Sure. Yep. That would be fine. Reduced first, right? Before you can make that decision, but yes. If you get to the point where you've reduced the radicals and they're not the same, you can stop and just say nothing more to do or whatever. So let's say we have okay. So let's say we have 180 plus 5 square root 135 minus 2 square root 80. So I'm going to start just by doing prime factorizations of these things because looking at them, I don't see any obvious perfect square multiples in there right off the bat. If I can't see it right away, I'm just going to go to the prime factorization because it's probably going to be the same amount of time as searching for the perfect squares. So 180 is 2 squared times 3 squared times 5. 135 is, oh shoot. can I change that to 125? I'm sorry, guys. 5 to the third is 2 to the fourth times 5. So far, so good. So if I look at the first radical, I can take out a 2 and we agree? The second radical, I can take out a 5 and I'm left with still 1 5. Everybody good with that? And I look at the last radical and I can take out 2 2's, right? Because 2 to the fourth is really 2 squared and 2 squared. So now I have 3 2's on the outside and the 5. So far, so good. Plus 25 root 5 minus 8 root 5. 6 plus 25 is 31. Minus 8 is 23. So the nice part about the adding and subtracting is it's really no more difficult than just reducing a bunch of radicals. And if they're the same, we just add the coefficients. And if they're not the same, then we don't have anything to do. What do you guys think? Doable? Okay. Do you want to see more examples, or you feel like you're ready to practice on your own? Ready to practice? So we'll stop here. In the content